Hi, everyone. So today is integrals part 2. We're going to go over a couple practice problems to see what these integrals are going to look like when we start doing them for physics problems, right? So first, we have a sled accelerates according to this function. A of t equals 3 meters per second cubed t plus 5 meters per second squared. Its initial speed is 12 meters per second, and its initial position is positive 15 meters. Find expressions for v and t. Then how far from the origin is the sled at t equals 2 seconds? So remember that when we're solving for the integral of acceleration is velocity, integral of velocity is position. So let's rewrite the function real quick. Got a of t equals let's see, we've got 3t plus 5. And remember, we were given the units, meters per second squared. Even that 3t has the unit meters per second cubed, because if you take meters per second cubed, multiply by a unit of time, you would get meters per second squared. So let's take the integral of that, which would be v of t. Right? We can actually write that real quick. Integral of a of t will give us v of t. So then we take the integral of 3t, which would be 3t squared over 2, right? Add 1 to the exponent, then divide by that same exponent, plus 5 times t. You just give it the variable that it needs, plus c. And we're also given the information that v naught equals 12 meters per second, which is enough information to solve for c, right? That means that v of 0 at 0 seconds is 12. So if we put 0 in for each t, that would be 0 here, plus 0 here, plus c. So 12 equals c. Now, when you start thinking back to math, when you have a function, right, and you have a constant at the end, that constant is going to describe initial conditions, right? So when you have a velocity, acceleration function, something along those lines, that actually tells you, if you look at the constant in the function, what the initial value is. So for example, if we look up here, we have 3t plus 5. That tells us that the acceleration, initial acceleration is 5 meters per second squared. And then with every second after that, it increases by 3. So that's what that tells us. Now, if we take the integral of v of t dt, I didn't put dt up top, my bad. That would equal s of t. That is your function for position. So let's find that. S of t, let's take the integral of what's above. We have 3 halves t cubed divided by 3 plus 5t squared over 2 plus 12t plus c. And we are given the information that initial position is positive 15 meters. So let's simplify this first, right? That 3 can go away right there. So then we have s of 0 equals 0 cubed over 2 plus 5 over 2 times 0 squared plus 12 times 0 plus 15. Sorry, jumped the gun. Plus c equals 15. So then all of the zeros cancel, right? This is gone, this is gone. Then you are just left with c equals 15. So then we can rewrite our function. S of t equals t cubed over 2 plus 5t squared over 2 plus 12t plus 15. Or using the information that we just discussed, if you know the initial value, you can just plug that in for C. That will be your initial value for the physics problem, and it will be your constant in the function. Now, part B, right? It asked how far from the origin is the sled at t equals 2 seconds. So we're looking at distance. The position function is going to tell us distance. So if we use s of 2, that tells us the position at 2 seconds. So let's see, we have 2 cubed over 2, right? Plus 5 halves times 2 squared, plus 12 times 2 plus 15. And that would equal, that's what, 8 halves plus 20 halves plus 24 plus 15. So that's 4 plus 10, 14, 34, 38, 48, 53. 53 meters. So 53 meters is our answer to part B. Good, so that is how we can use integrals to solve a physics problem when it gives us the function like that. Next, now we have the calculus for a rifle. So the speed of a bullet shot from a gun is governed by this equation. V of t equals -5 times 10 to the 7th t squared plus 3 times 10 to the 5th t, where v is in meters per second and t is in seconds. Now wants the functions for position, acceleration, and jerk, which means that we're going to have to go both directions, right? So we will have to take the integral to go from velocity to position, but then we'll take the derivative to go to acceleration and acceleration to jerk. Then B asks, if the bullet's acceleration is 0 at the end of the barrel, how many seconds is the bullet accelerated? Then C asks, assuming the bullet leaves the barrel at that time, what is its speed at the end of the barrel, and what is the length of the barrel? Oh, and I have a typo there. So let's get that equation down real quick before we start our math. V of t equals -5 times 10 to the 7th t squared plus 3 times 10 to the 5th t. Okay. Good deal. Now, let's find position first. That's what we've been solving for lately, so that we can do our integrals. And then we will go on from there. So the integral of v of t dt would be s of t. So we would take -5 times 10 to the 7th t cubed over 3 plus 3 times 10 to the 5th t squared over 2 plus c. Right? Now, we already know the initial value of the bullet, right? The initial value of a bullet is 0, right? At time 0, when it's fired, it's not moving. So we can actually call that a 0. That's also the position, initial position is 0 at the beginning of the barrel. So that gives us initial velocity, initial position, because you can also say over here we've got a +0 for the initial conditions, like we talked about before. So there is our position function, right? You can also, so looking at scientific notation, you can actually say that is -5/3 times 10 to the 7th. And then this is 3/2 times 10 to the 5th. That's legal to say with scientific notation. You can just manipulate the initial value in that scientific notation to get what you're searching for. So that's legal. Now that's s of t, right? Now we need a of t. So instead of taking the integral of velocity, we'll take the derivative of velocity with respect to time to get a of t. So the derivative, right, we would take 2 times -5 times 10 to the 7th, then subtract 1 from the exponent. Then there is just a 1 as an exponent, so that is 3 times 10 to the 5th. Take the t away, and there's no constant there. So that is our acceleration. We could do this multiplication, negative 10 times 10 to the 7th t plus 3 times 10 to the 5th. You can also say that is negative 1 times 10 to the 8th, whichever floats your boat. I did make a mistake, though, because here we need to have our units. We were given units before. We have to have units in our answer. So this would also be meters per second squared for that entire function. Right? So that is our A of t. Now to find, it asked for jerk, right? It did. Okay, so then we find the derivative of acceleration with respect to time. That would give us the jerk function. So let's take the derivative of this. The derivative of that is just negative 10 times 10 to the 7th, and then the other is a constant. So that is our meters per second cubed, and that is all we have. And remember, you can also say that is negative 1 times 10 to the 8th meters per second cubed. Also an acceptable answer. Now, part B asks if the acceleration is 0 at the end of the barrel, how many seconds is the bullet accelerated? So what we can do here is set acceleration to 0 and solve for t. So let's do that. Our acceleration function, okay, we're going to set to 0. And then we have, we'll do negative 1 times 10 to the 8th t plus 3 times 10 to the 5th. And that is all in meters per second squared, right? Now let's solve for t. We subtract the 3 times 10 to the 5th to the other side. Minus 1 times 10 to the 8th t. Now divide. So then you would have negative 3 times 10 to the 5th divided by negative 1 times 10 to the 8th to give you t. Put that into your calculator. Or you can just do the exponent math. So that would be, actually, let me show you how to do that. So you can take negative 3 divided by negative 1 is 3. Then you take 5 minus 8. You take the top minus the bottom in those exponents, and that would give you negative 3. 3 times 10 to the negative third seconds. That is 0.003 seconds. Or anytime you see 10 to the negative third seconds, you can call that milliseconds. All of that is acceptable. Good. So that's how long the bullet was being accelerated. Now, assuming the bullet leaves the barrel after that time, 3 milliseconds, what is its speed at the end of the barrel, and what is the length of the barlay? So remember, we can also just take that time, plug it into velocity and position. So our velocity function for 0.003, okay, that will look like negative 5 times 10 to the 7th times 0.003, and that will be squared. Then you have 3 times 10 to the 5th times 0.003. That is going to equal 450 meters per second once you put that into your calculator. Then it also wants position, the length of the barrel, right? So let's find the position at that time, and the position of the bullet at that time would be leaving the barrel, so then we can see how long the barrel is. So this will be negative 5/3 times 10 to the 7th times 0.003, and that will be cubed, plus 3/2 times 10 to the 5th times 0.003, and that will be squared. Now, once you put that into your calculator, you will get 0.9 meters or 90 centimeters, both acceptable answers. That's So that's a pretty long barrel. When we can see that's a rifle, but almost a meter long, it's a long barrel. So that is how you can use calculus to solve for this kind of scenario where you're given velocity. You take the integral to get position, derivatives to get acceleration and jerk, and then plug in values to find the requested scenarios and things like that. All right, so this one is a little bit more complicated. The velocity of a bicyclist at the start of a hill is given as v of t equals 0.75 t squared plus 5 meters per second. Her initial position is negative 50 meters from the finish line. 1, how fast is the bicyclist going at the start of the hill? We want the initial velocity. What is the rate at which her acceleration is increasing on this crazy hill? So that means that we're actually going to have to find rate of change for acceleration, which is jerk. Then how long until she crosses the finish line at the bottom of the hill? So then we will need time for position. Then what is her final speed as she crosses the finish line? So we'll take that time, put it into velocity. Okay, so we can do this. Let's see, we've got v of t equals 0.75 t squared plus 5 meters per second. So first we want to know how fast is the bicyclist going at the start of the hill. Well, if you put 0 in for t, you'll get 5 real quick in that equation, or you can just use that rule that we used before. Just look at the constant. For number 1, the answer is 5 meters per second. We know that just by looking at the equation. Okay. Then for number 2, we want to know what is the rate at which her acceleration is increasing. So that is going to be jerk. So we will take the derivative of velocity with respect to time to get acceleration. So then we have 0.75 times 2, that's 1.5 t. And then the 5 just goes away. So that is our acceleration. That is not our answer, but that is key, right? Because then we need the derivative of acceleration with respect to time, which is our jerk. And that would be 1.5 meters per second cubed. And it asks for the rate at which it's changing. That is it. It is changing at 1.5 meters per second cubed, which is a crazy hill. Now for number 3. This one's going to be tricky. This is the hard one. It says, how long until she crosses the finish line at the bottom of the hill? So what we need to do is we need to find the position function, and then we know that she's 50 meters from the finish line, so see how long it takes her to travel those 50 meters. So we have the integral of v of t dt, which would give us the position function, right? So we are integrating, let's remind ourselves, what are we integrating? It's 0.75 t squared plus 5 dt. So to integrate that, we take 0.75 t cubed over 3 plus 5t plus c. And then we can simplify that to give s of t, that's 0.25 t cubed plus 5t. And we have the initial position, right? Initial position is negative 50 meters. Looks like the finish line is at the 0 position. For some reason, it was measured like that. So that means that we have minus 50 here. And then you put your unit on there because the whole thing is meters. Now, again, not the end of our problem. Here, this gets complicated because then we need to find t when the position is 0. So when you set that equal to 0, we find 0.25 t cubed plus 5t minus 50. Now, if you're going to do this for homework, a problem like this, I would recommend using Wolfram Alpha to try and solve this one. This is pretty tough. If this was on a test, what I would do is I would graph it on a graphing calculator and try to find the 0 value. Your 0 value is, I believe, about 4.25. I'm sorry, your initial value is about 4.725. So t equals 4.725 seconds. That is about how long it takes her to cross the finish line after she starts going down this hill. So no time at all. Now, that one's pretty tough to do algebraically. I don't recommend doing that one algebraically. I would do that one graphically, or if you have a super calculator like wolframalpha.com, you can use that, unless it's a test. Don't cheat. Now, number 4, what is her final speed as she crosses the finish line? Well, we take v of 4.725. Our v equation is 0.75 times, 4.725 squared plus 5. So if we do that math, we get 21.74 meters per second. So that's how we can solve those problems. Now, when they get into the cubic land, it's really complicated to solve that algebra. So this was an unfortunate problem writing accident by myself. I overcomplicated the problem when I wrote it. But that is how we can use these practice problems to get some experience in solving integrals. That's all we have for the integral practice, and that ends chapter 6. So then we will move on to chapter 7 next.